Hello everyone, welcome to Computer Science 318, lecture number 6. Okay, I'm really hoping I'll be able to see you in person next week. Okay, today we'll be talking about AVL trees. Okay, it is something which you're not technically supposed to know about trees from 227. Okay, so it's technically there'll be new material. Okay, um, please take a quiz today and read chapter 1 again of your textbook, which recaps basic data structures. Okay. So the first question, like why we'll be talking about those trees, is what is the longest it can take to insert an element into a tree with n elements? Okay, so basically imagine you have like a binary search tree or just a tree with n elements, um, and like so like let's draw that. Okay, so let's say we have a binary tree, for example. Okay, let's imagine we have something like this. Okay. So in this case, again, assuming that you're going to pay me $1 every single time I'm going to be comparing the new element, right, to the element I'm comparing that to. So if I'm inserting right, I start from the root and then I just go left to right. If it's a binary search tree. Anyway, so assuming you're going to pay me $1, how many dollars, if you have like n nodes, how many dollars you're going to pay me for inserting an element? Okay. So again, we're thinking about the worst case scenario, the longest. Okay. So what is the biggest amount of money you're going to pay me? And the answer is going to be n. Okay. At most, if I have a tree with n nodes, you're going to pay me n dollars. Why? It's possible in the case if I have something like this. If my tree looks like that. Imagine it's a binary search tree. Okay. And it's just basically one straight line like that. Okay, so for example, it's 0, 1, 2, 3, 4, 5, 6. Okay, so the whole thing is just one line, okay? And I'm trying to insert, let's say, -1 here. Okay, so starting from 6, going to the left to 5, going to the left to 4, okay? And the new node will basically have to become the left child, right? You'll have to become like this. Okay, so that's how it works. Cool. Okay. Yeah. So again, the answer would be n. Okay. So it will be big O of n. Okay. Now another question would be the opposite. What is the best case scenario for inserting an element into a tree? Okay. So imagine you have like something similar. Okay. And then what if again that's going to be -1 and that's going to be 6. What if I'm trying to insert 7? Okay. In this case, this new node immediately comes to the right child of the root. Okay. And then basically becomes 7 goes over here. So in this case, you just spend $1. Okay, so no matter how big the tree is, okay, no matter how many elements I have here, you're going to pay only $1. You're only going to pay for one comparison, the node to the root, and that's it. Okay, so it's going to be technically in computer science it's called big O of 1. Okay, and big O of n. You don't really have to think about in the terms of big O. You can just say like n or just 1. Okay, but you see that it's unfair, right? So like it's super unfair to have something like this because kind of it's such a huge difference between the worst and best case scenario. Okay, and why is that? Is because this tree is kind of like very skewed to the left, right? So it'll be much better if we had a tree like this. So each node would have like which would have 2 children, okay, and it'll be kind of like more leveled. So if we had something like this, they'll be much more fair, right? Because in this case, the worst case scenario we would just insert a node here, and the best case scenario we would insert a node over here, okay? And the difference between the best and the worst case scenario isn't that big, okay? So that's kind of what balancing is all about, and those AVL trees which we'll be discussing today, they're also about that. So how do we keep them balanced? Okay, so AVL trees are well balanced. Okay, so you're not going to have that situation where just one straight line with AVL trees. In an AVL tree, the difference between the heights of every node's 2 subtrees is either 0 or 1. Okay, so again, the difference between the heights of 2 subtrees is either 0 or 1. Okay, it can be shown that the maximum height of AVL tree is big O log n. The process of inserting and deleting a tree in AVL tree is the same as in regular binary search tree, except that you may have to rebalance the tree after an insertion or deletion operation. Okay, so for example, here's an example like this guy over here. That'll be a good example of a balanced tree. Okay, the AVL tree which is balanced, right? So if you take a look at any node, any particular node, okay, you'll be able to see that, for example, I don't know, let's take a look at this node, okay. The height of the left subtree and right subtree is either the same, okay, in this case it's exactly the same, or the difference between the heights is 1, okay. So if I take a look at this node, for example, the height of the left subtree is, well, I guess it's 1, right? And the height of the right subtree is 0, okay? So it's not the difference is either 0 or 1, right? If I take a look at the root, okay, what is the height of the left subtree? 1, 2. What is the height of the right subtree? It's just 1, okay? So the difference between 1 and 2 is 1 or -1, okay? So again, this tree would be balanced, considered to be balanced, and that's an example of AVL tree. The process of inserting or deleting an element is the same, okay, except for the fact that you may have to rebalance the tree after you inserted an element or deleted. The balance factor, okay, it's a technical term, of a node is the height of its right subtree minus the height of the left subtree, okay. The node is said to be balanced if its factor is either 0 or 1 or -1. A node is left heavy if the balance factor is -1, and right heavy if the balance is +1, +1. Okay, so again, balance factor would be the height of the right subtree minus the height of the left subtree. Okay, should I give an example? Well, yeah, okay, let me draw an example. Okay, so let me make it bigger. Okay. Well, okay, yeah, let's keep it this way. Okay. Okay, so let's try to calculate the balance factor for each of those nodes. We're going to start at the bottom. Okay, so the balance factor for this one is, again, is the height of the right subtree minus the height of the left subtree. There are no right subtree, there is no left subtree. That's why the balance factor is 0. Same thing over here. Same thing over here. Okay, now let's talk about this node. Height of the right subtree, which is I don't know, I guess also 0, minus 0 is 0. Okay, and now if we take a look at this node, the height of the right subtree, okay, is 0. The height of the left subtree is -1. Sorry, a 1, right? So in this case, 0 minus 1 is going to be -1. Okay, so we calculated the balance factor for each of the nodes, okay? And if we see only zeros and ones and -1s, in this case, that tree is considered to be balanced. Okay, so in this case, again, this tree is balanced. Now, if we try to make it unbalanced, if I create one more node like this, okay, then everything is going to be changed now. So the balance factor for this node is 0. Okay, this one is 0. For this one, it's already -1. Okay, so here it's different. For this guy, it's already -1. Okay, so the height of the right subtree minus the height of the left subtree. Okay, it's going to be -1. For this one, it's 0. For this one, it's going to be -1 as well. Okay, we have one edge on the right, two edges on the left. So it's going to be -1. For this guy, it's the same. Now, let's talk about this one. So for the root, okay, on the right, we have one edge. On the left, we have 1, 2, 3. 3 edges. So 1 minus 3 is going to be -2. -2. And yeah, so this tree is already, according to the definitions of AVL trees, this tree is not balanced, okay, and it needs to be rebalanced. Okay, so whenever you have -2 or +2, it's a huge problem and you need to work on that. Okay. So if a node is not balanced, okay, after an insertion or deletion operation, you need to rebalance it. The process of rebalancing is called rotation. Okay, there are 4 possible rotations: LL, RR, LR, and RL. Okay. So let's take a look. Here's an example of LL rotation. Okay, so we have like 4 types of rotations. Okay, here's and they have like kind of like the really weird names. The way I remember them is the following. Okay, so imagine you have a tree like this. Okay, and let's say again, so the A is root here, but technically it doesn't have to be root. Okay, it's possible that it has some parents. Okay, it has something on the top. So, well, first off, AVL trees are only about binary trees, not necessarily binary search trees, but always binary trees. Okay, so you may have at most two children, two subtrees. Okay, so we have an A, we have B. Okay, now let's imagine that B has two subtrees. Okay, the height of the left subtree is h plus 1, the height of the right subtree is h, the height of the right subtree for A is also h. Okay, so how, like when I'm looking at it, how do I know that I need to perform LL rotation? The way I remember that is I'm just trying to find the node which is not balanced. Okay, so in this case, let's calculate it. So here we have the whole height of this tree is h, the whole height of this subtree is h plus 1. Okay, so for the B, what are we going to have? H minus h plus 1, so it's going to be negative 1. Okay, so which is still fine. Okay, so it's technically B is balanced. Okay, and then when we're looking at A, what are we doing? We are doing H minus H minus 1 and also minus 1. So for A, the balance factor is going to be negative 2. So I'm finding the node which is not balanced, and then I'm looking at from that node, I'm trying to look at the subtree which sticks out. Okay, so what's causing problems here? Like, where is the problem? And the problem is this guy, right? So this guy is too high, is too tall, right? It has like too many edges. How do I get from here to here? I take one step left, one step left. Okay, so that's how I remember kind of for myself what kind of rotation to make. LL means that again from the node which is imbalanced, I take one step left, and here have the stuff which sticks out. Okay, so this particular guy is sticking out. Okay, cool. Okay, so an LL imbalance occurs when a node A such as at a node A such that it has a balance factor of negative 2, and the left child B with a balance factor negative 1 or 0. This type of imbalance can be fixed by performing a single right rotation. Okay, so the whole idea is that we need to go from here to over here. Okay, so how to do that? I mean, I'm not sure how. I look at the book and look at how they explain it. I don't think it's honestly that easy to follow. So I'm going to give my kind of alternative version of how to do that. Okay, so here's what I'm going to do. Maybe I'll do it like this. Okay, so here's the way I remember. So what we're going to do, we're going to rotate this tree. Okay, here's the direction of how we're going to do it. Okay, so we're going to go like this. Okay. Okay, so that's how we're going to rotate it. We're going to take this whole thing and we're going to just like kind of rotate it clockwise. Clockwise, yes. Okay, so in this case, what's going to happen? We're going to bring B up and we're going to bring A down like that. Okay, so B is going to become the kind of the root or subroot, okay, because again, it's possible that A is also not the root, A is located to something else, okay, it's connected to another node, and then there is one more maybe. Okay, so again, it's possible this whole thing is only part of the tree. Okay, so we're going to bring B up and we're going to bring A down, okay, and then, so again, like, and then after that, once you understand it, I think it's more or less easy to understand what's going to happen next. Okay, okay, so we are bringing B up, we bring A down, okay, perfect, got that. That's B, that's A. And now let's see, what do we have left? We have T1, T2, T3, okay? And the whole thing is that by the end of our rotation, the whole thing has to be balanced, okay? So we have, if it is a binary search tree, okay, let's see. The whole thing why I did this is I want to bring T1 one step up, okay? And T1, where can it be located? Okay, it was located on the left from B, and that's why if it is a binary search tree, the values here are less than B. That's why the only place it can be located at is still on the left from B. Okay, so T1 still has to be located here. Okay, so this is still T1. Okay, now what about T3? T3 was located on the right from A. It was located on the right from everything, right? So that's why T3, if it is a binary search tree, contains the biggest values. That's why I, right after a rotation, in order to keep the same property, right? T3 also has to be on the right from everything, which means it has to be on the right from A, okay, which means it can only be here. That's our T3. Okay, and what was the difference between T1 and T3 in terms of the height? The difference was 1, right? So T1 is 1 level higher than T3. Okay, so now they're kind of equal to the same. Okay, cool. Next, and here we have only T2. Okay, so where's T2? T2 used to be the right subtree of B, but now it can't be there anymore because it's now B, right subtree of B is A. Okay, so where can it go now? It has to be between T1 and T3. Okay, so definitely somewhere here. Okay, and now where else can it be? It has to be on the right from B. Okay, and on the left from A. So the only place it can be at is here. T2, like this. Okay, so that's the rotation. And now if we take a look at, again, the heights, okay, so the height of T2 and T3 are H, okay, and they're located on the same level, and the height of T1 is H plus 1, okay, so it's kind of, so this one becomes perfectly balanced, and now the balance factor of everything is 0, basically. Okay, so that's LL. Okay, hope it makes sense. Okay, moving on. Same thing, but to the opposite direction, RR. Okay, so again, I'm looking at this tree. Okay, I'm looking at the node which is not balanced. One step to the right, one step to the right. Okay, this guy sticks out. This guy is giving us issues. This guy is giving us problems. Okay, so we need to rotate it. Basically, going to do the same thing, but in the opposite direction. Okay. So what am I going to do? I'm going to take what? I'm going to take this guy. Okay, boom, like that. Okay. So I'm going to take the whole tree and rotate it that way, rotate it counterclockwise. So I'm going to bring B up, okay, and I'm going to bring A down, like that. Okay, and again, just I think the easiest way of thinking about it is not memorizing, but just thinking logically. Okay, so I'm bringing B up. Okay, I'm bringing A down. Gotcha, cool, makes sense. Now let's think about what's supposed to happen to T3, T2, and T1. Okay, so T1 has the highest values. It has to be on the right of everything, which means it has to stay on the right from B. Okay, so which means T1 is here. Okay, now T3 has the lowest values of the entire tree, so it has to keep staying on the left from A. Right. So T3 is here. Okay, and now T2 has to be somewhere in between. Okay, so it used to be on the left from B, and that's how it's supposed to stay, right? So it's going to be on the left from B, and it has to be on the right from A. Okay, so on the left from B, on the right from A, so it's going to be here. Okay, so T3, this height is H, this height is also H. Okay, so these guys have the same height, and this guy has the same, the height of is H plus 1. Okay, that's why, again, they have exactly the same level, so the balance factor is the same. Well, the balance factor of everything is 0 now. Okay, cool, hope it makes sense. Let's keep it going. Now we're coming to something interesting. All LR. Okay, so again, I'm looking at the balance factor. I'm looking at the tree, looking at the balance factors of each node. I'm finding the one which is causing the biggest amount of problems. Okay, this guy A. Okay, how do I find the one which sticks out? One step to the left, one step to the right. Okay, so that's the situation for LR rotation. Okay, so what what can I do with it? Okay, so well, again, so C has like the bounce factor of 0, right? So H here, H here. In terms of B, we have +1, okay, because the right subtree is one level higher, okay. In terms of A, we have how many edges here? 1, 2, 3, and H, okay, and here we get only 1 and H, okay, which means H plus 1 minus H plus 3 is going to be -2, okay, so the balance factor for A is -2. So what are we supposed to do here? So that's not LL, it's not LR. There are a couple of ways of doing it. Again, I just go a bit unconventional. So the book is, I think, suggesting is to perform double rotation. Okay, so like one rotation to the left and one rotation to the right. Okay, I don't really like it, honestly. I think there is like much, especially because again they just like kind of focus on memorizing versus understanding something. So here's my philosophy. Here's what I recommend. Although you can of course follow the book version of explanation. Here's the way I memorize it. I just memorize the fact that I need to bring C up. Okay, so that's what I need to do. I need to bring the C up. Okay, and that's it. Okay, so I'm going to bring the C up, and I'm going to see what's going to happen. Okay, so that's kind of my philosophy. So again, this guy sticks out. I'm going to take the root of what sticks out here. I'm going to bring it up. Okay. Am I correct? Yeah, perfect. I'm correct. Okay, cool. So let's see. I'm going to bring the C up. Okay, C is going to be here. Now let's see what happens. C is going to become my root. Okay, get that. Now, what can be on the left? What can be on the right? So B was on the left from C, right? So it's going to stay here. Okay, A was on the right from C, technically, right? That's why A is going to stay there also on the right. Okay, and now let's see what happens to T1, T2, T3, T4. The easiest things to discuss first are T1 and T4. So T1 contains the lowest values of in the entire tree. That's why it has to be staying there to the leftmost side, right? So T1 was on the left from B. That's why it has to keep staying on the left from B. Okay, so T1 is here. Okay, so T4 used to be on the right from A, and just basically on the right from everything. That's why it has to keep staying there. It has to keep staying on the right from A. Okay, so T4 has to be staying here. That's the only place where it can fit. Okay. Next, T2, T3, that's a bit interesting, right? So we can't really connect it to C anymore because C became the root, right? So we basically have to connect it, like we only have two places left. Okay, so right from B and left from A. Okay, so now let's see what fits where. What fits where? Okay, this one is T4. Okay, so T2 has to be on the right from B and on the left from C. Okay, on the right from B and on the left from C. So it's here. It's this guy over here. T3 has to stay on the right from C and on the left from A. On the right from C, on the left from A. Yeah. Perfect. Yeah. So that's how it works. Okay. So in my opinion, that's the easiest way, again, to understand it versus like memorizing something. Because of course, understanding everything is much better than memorizing everything. Cool. Moving on. Dun, dun, dun. And the last one is RL. Right. Last one is RL. Same thing, again, just the opposite direction. Dun, dun, dun. Hold on. I'm gonna take that. Okay. Yeah, cool. Ready. Okay, so RL again. Finding the node which has the balance factor outstanding balance factor. Okay, so A has the balance factor of 2, positive 2. Okay, so positive 2 is a problem. Now, where's the node? Where's our problem? What sticks out? Okay, so one step to the right, one step to the left. Okay, so here's the C, and everything below C sticks out. Okay, so again, here we have H, here we have H. So C, balance factor of C is 0. If here we have H, then H minus H plus 1. Okay, the balance factor of B is going to be -1. Okay, now if here we have H also, the height of this subtree is H, then this is going to be H plus 2, right? H1, 2, okay. So H plus 1, H plus 2, okay. So H plus 2 minus H, so the balance factor of A is going to be positive 2. So this is our standard balance factor. Okay, so again, where is our problem? One step to the right, one step to the left. Okay, RL. So same strategy. Okay, we're going to take C and we're going to bring it up. Okay, and we're going to make C the root. Okay, here's what, so we're going to make C the root. C is going to be our root. B is going to be on the right from C. Okay, so B is here, and A is going to be on the left from C, right? Just in order to keep the whole binary search tree properties in place. Okay, so C is on the root, A is on the left, B is on the right. Okay, perfect. Next, again, we have 4 subtrees, T1, T2, T3, T4, the height of which each one of them is H. Okay, we just need to like spread them out. Again, the easiest ones to discuss first are T1 and T4 because they have the lowest values of the entire tree and the highest values of the entire tree. Okay, so T1 is going to be here, T4 is going to be here. Okay, no problem. Okay, T1, T4. Okay, and now we have T2 and T3 left. Okay, they have to be somewhere in the middle. Okay, now we have only 2 placeholders basically to place them into. Okay, on the right from A and on the left from B. Okay, so where do we place what? So T2, it has to be on the right from A and on the left from C. Okay, on the right from A, on the left from C. Okay, so T2 is here. T3 has to be on the right from C, on the left from B. Okay, right from C, left from B, so it's here. Okay, that's it. And in this case, again, the height of T1, T2, T3, T4 is still H, right? So the balance factor of every single node is going to be 0 here. Hope it makes sense. Hope it makes sense. Hope it makes sense. Okay, so moving on, let's do a very quick exercise. Please pause the video and insert into completely blank binary tree 14, 17, 11, 7, 53, 4, and 12. Okay, so we're talking about binary search tree. Okay, and the whole strategy is that, yeah, so just insert them all. Insert them all. Okay, so pause the video, insert them all on the paper. Okay, cool. So I'm going to assume that you've done it. Now, please insert 13. Okay, and now let's see what's going to happen here. So you should have something like this: 14, 7, 17, 4, 11, 12, 13. Okay, so that's a problem. Okay, of course, that definitely sticks out. Now we need to do something. Okay, so how do we balance that out? We need to, first off, we need to write out the balance factor for every single node. Okay, for every single node, we need to write out the balance factors. Okay, so it's 0, here it's going to be 1, here it's going to be 2, here it's going to be 0, here it's going to be 0. Okay, here it's going to be 1, here it's going to be 1, 2, 3 minus 1, it's going to be 2. Okay, and here 1, 2, so 2 minus 1, 2, 3, 4. Okay, so 2 minus 4 is going to be -2. Okay, so broad balance factor for each one of them, and then we're going to find, starting from the lowest, we're going to balance everything out. Starting from the lowest. Okay, so we're going to balance it. Okay, and okay, so again, starting from the lowest, right? So we're looking at this. The one which sticks out again, so the lowest node which has the run balance factor is 11. It is 2. Okay, so we need to perform our rotation here. Okay, so we need to bring 11 down, 12 up, okay, and 13 up. Okay, and in this case, it's going to look like this. Okay, so now this is going to be more balanced. Okay, so now let's do the same thing. Let's write down the balance factors. Okay, so 0, 0, 1, perfect. That's good. 0, 0. Okay, now here it's going to be 1. Here it's going to be also 1. Okay, here we're having 1, 2, minus 1, 2, 3. Okay, so that's going to be negative 1. Right? Okay. Now insert 8. Okay, so again, for this one, we have it balanced. Okay, everything is fine. Now we're going to insert 8. Okay, so where is 8 going to get? Over here, 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 here. Okay, so 8 is going to become the left subtree of 11. Okay, like this. And that breaks everything. Okay, so now we're going to have to balance it most likely. So let's write balance factors for each node. 0, 0, 0. Okay, so for this one it's negative 1. For this one it's also negative 1, right? So 1 minus 2. Okay, so for this one it's 1. For 7 it's going to be what? 1, 2, 3 minus 1. So 3 minus 1, that's 2. For 14 is going to be 2 minus 1, 2, 3, 4. Okay, so it's negative 2, right? Negative 2. Okay. Yeah. Okay, so we need to balance it. Okay, so we need to find the node which has the unbalanced factor. It's going to be 7. Okay, and now let me double check. Hold on. So 0, 0, negative 1. Here it's also negative 1. 1 minus 2. Okay. Here we have the height of this subtree is 1, 2, 3, 1. Okay, that's 2. Okay, and for this one it's 1, 2 minus 1, 2, 3, 4. Okay, negative 2. Yeah, right. Okay, so we need to balance the whole thing around 7. Okay, and that's going to be what? What sticks out? Right, left. Okay, RL rotation. RL rotation. Okay, now we need to balance it. Okay, and what we're going to do here, we're going to bring 11 up. Okay, so again, so these slides show how to do it according to the book. Okay, so according to the book, you need to perform the right rotation first. So you need to bring 11 up, okay, and then 12 down. Okay, so it's going to be like this. And then after that, you need to rotate the whole thing to the left. Okay, and it's going to be like this. Okay, just according to my methodology, which in my opinion is a lot easier, what we're going to do, we're going to bring 11 up like this. Okay, so in this case, we're going to have 14 is in the same place, 17 is in the same place, 53 is in the same place. Okay, okay, and then after that, we're going to bring 11 over here. Okay, bring 11 over there. Now 7 will go to the left. Okay, let me just hold on, make it aligned with 53. Okay, 7 will go over here. No, still not perfect. Like this. Okay, so I'm bringing 11 up. 7 will go to the left. 12 will stay here. Okay, like this. And now we have 4, 8, and 13. Let's distribute them. 4 is the lowest. Okay, so it's going to be on the left. 4 is here. 11 brought up. 12. We have 13. 13 is the highest, so it has to be here. Okay. And now what's left here? It's 8. Okay, so where is 8? Where does 8 fit? Okay, it's either on the right from 7 or on the left from 12. Okay, So 8 has to be on the left from 11, right? And yeah, so basically the only place it's going to fit is here. And that's going to be our 8. Okay, like this, and now everything is going to be balanced, I think. Okay, so now if I take a look at this tree, okay, I try to calculate the balance factors for each one. Okay, let's see. So we have 0 here, 0, 0, 0, okay, 1, 0, 0, right? So 2 here, 2 right, on the right, 2 on the left, 1 here, okay, and 2 on the right, 1, 2, 3 on the left, -1, right? Perfect. Okay, so now this tree is balanced. So every single time we're deleting, if we have a tree, binary search tree, every single time we're deleting a node or inserting a node, we need to calculate balance factor for each one of those nodes. We need to perform the rotation in order to keep it balanced. For your for your homework, I'll ask you to write the binary search tree code. It's not going to be AVL tree, so there will be no rotations. But you'll need to remember how to insert and how to delete. Okay, delete is very important. How to delete nodes in Java. Sorry, how to delete nodes in a binary search tree. How to do that? Okay. Um, Perfect. Okay. Awesome, guys. Hope it makes sense. I'll see you guys later. Have a good one. Bye bye.